Okay, see if you can set that up. There's a region bounded by those curves. And see if you can just set up the integral. Yeah. Oh, yes, I switched these. Oops. So that should be X, this should be Y. Right? So, yeah, that's the lower bound is the X-axis and revolved around the Y-axis. Thanks. And you're doing it in shells. Sorry. That's what we're practicing. Do it in shells. So, right now it's impossible for you to do it the other way. We have people chiming in. I don't know why, but I'm just going to ask you if you get it correct or not. So, after we put it up. So, I should just ask you if you know it, and you'll be like, "Oh yeah, sure, I know it." No, we're not going to do that. Who'd like to start off with a prayer? Thanks. What's your name? Sorry, what? Andrew. Thanks, Andrew. Thank you, Andrew. Okay, a few quick announcements. You have the second project coming up. It is a problem. So the problem is to find something that you can find something where you need to use calculus to find the volume of. You can take a picture of it and do it in GeoGebra. I showed you guys how to do it. There's also instructional videos on Learning Suite on how to do that. You don't have to take a picture of it. You can do it in another way. Some students have asked me questions just as we've been doing volumes. They've asked questions like, what if the axis that you're rotating around isn't like this or like this? What if it's on an angle? And if you want to try something like that for your project, you're certainly welcome to. Or what if it's actually your axis is in the middle of your shape? Then when you spin it around, you get some stuff that gets counted twice. And you've got to really think carefully, a little more carefully about what that volume would be. If you want to do something like that, you're certainly welcome to. But I'd like it if you found something realistic. Give you a chance to think about modeling and how to take something in the real world and apply that. So that's the first announcement. The second announcement is, I forgot. No, oh yeah, okay, I remember. I hope you're getting help outside of class if you need help. The math is we're gonna have some sections coming up like 6.4 that are a little bit more intense than 6.2 and 3 and 1. I haven't had a lot of students come to my office hours. They're at 4 to 5 every day. Although Tuesdays, I have to miss a few more Tuesdays, and next week I have to miss Tuesdays and Thursdays. But yesterday, I didn't have any students from my class in office hours, and I spend an hour in the math lab helping other people's calculus students. So I'd love to help you more than someone else's calculus students, although it's still helpful. So please come. I'm a much better tutor than I am a teacher. The TAs are great. They can help you out fantastic. If you can't come to my office hours, come to, make sure you get to the TAs. Make sure you're getting the help you need outside of class. Yes? Send me an email about which problems those are, okay, and we'll write up the solution for you. So, okay. Do you want to vouch that I'm a better tutor than I am a lecturer? Because I helped you in office hours once, right? Okay. I think, but I am much better a one-on-one or a small group. Like I'm much better getting help. So, okay. All right. So take maybe one more minute. See if you can set this up. Okay, I'm gonna write down what the setup is. So just be honest. If this is what you got, then go ahead and click A for being correct, and then B for incorrect, and then we'll talk about it. Okay. Is that what, did anyone get that? I hope so. Anyone to check my answer there? Okay, so click A if you got it correct, B if you got it correct. C if you wanted to get it correct, but you didn't. No. Okay. Make sure you click on one of them because that's how we're taking attendance. All right, a little bit about shells. So there's a way to think about, there's one simple way to think about shells and the disk method, shells and the washer method. Just one simple difference, okay? And that difference is whether you're thinking about rectangles like this, okay, that are perpendicular to the axis that you're rotating around, or whether you're thinking about rectangles like this, which are parallel to the axis that you're rotating around. Okay, in your region, you can chop it up this way, horizontally, you can chop it up vertically. Okay, if you do it one, you get shells. If you do it the other way, you get disks. Okay, and the difference comes from the shape you get when you start spinning those around. Okay, if I'm the axis, and I've got my meter stick here, if I slice perpendicular to the axis, I'm going to get small slices like this. The rectangles that I'm going to spin around look like this. And then if I spin, what do I get? I get a disc or a washer, depending on how far this is from the axis. Okay? But I can choose, instead of slicing up my region horizontally, I could slice it vertically. And then I've got rectangles like this. And if I spin around, what do I get? I get shells. I get these kind of tin can shaped things, no bottom and no top. Okay? We call them shells. Okay, so if you have rectangles like this, and you're spinning this way, you're going to end up with the shell method. So here your rectangle is parallel to the axis. If your rectangle is perpendicular to the axis, you spin, you're doing discs around. Okay? And it still works the other way. If you're going to spin it around the equivalent of the x-axis, if you chop it up perpendicular and spin this way, discs and shells. So your slices are perpendicular to your axis of rotation. If you slice it up in terms of y, when you're spinning around something like the x-axis, when you spin around, you get a shell. Okay? And because you get a different geometric shape, we have to use a little bit of different geometry to figure out what the volumes are of each of those slices. So I'm just going to draw this here again, and we'll walk through this problem. Oh, wait. Actually, let me do. Oh, yes. Brian.
So I understand to use x as the radius. You do the radius, you do it by the height, which is usually the function. And sometimes I just wonder why just and not like the number of what the radius would be. Sometimes it looks like the radius should be changing, but it's in x. Does that make sense?
Yeah. Let's get to that in a second. I forgot to show you good news. So let me turn on some lights. So here's a volume of rotation. If you slice, if we think about slicing this way, you can imagine a region right here. And you think about slicing this way, then you've got rectangles that you're going to spin around, and you end up with your shells like that. Okay. And I wish I had another big one for this, but here's a small one. And what we're going to do with these shells is, to figure out the volume, is we're going to cut them and then unfold them. And if you cut them and unfold them, then you end up with this. So this is supposed to be the exact same size as this, if you cut it and unroll it. Now, what does that look like? Looks like a rectangular solid, although it's not exactly a rectangular solid. It's off a little bit, yeah. But we're going to approximate it with a rectangular solid, and it's going to be close enough with the limit. So we're going to assume that these have straight edges, and we just need to calculate a height, we need to calculate a length, and we need to calculate a thickness. And our thickness will always be dx or dy. Okay, so let's do that. I'm going to draw one of those up here in our particular case. So here we're going to have a delta x or a dx or a dy in our case. In our case, we're doing with respect to y or with respect to x? We're doing it with respect to x because we're spinning around the y-axis or something that's parallel to the y-axis, and if we want shells, then our slices need to be something that's parallel to the axis of rotation. So as I spin this around, okay, I'm going to get, there's my poor drawing of a shell. So there's my shell. I need to figure out the volume of that shell. If I cut it and unroll it, it looks like this up here. What is the height of that shell? If this is x, this is an arbitrary x point, and this is an x distance. X is a distance. And this is the curve y equals e to the x. It's just the same problem we did for the quiz. So what's the height going to be at an arbitrary x coordinate? It's going to be e to the x. That y value, that height there, or that function value, is what I get out when I plug in an x and evaluate it. And as the exponent of e, I plug it out, it's going to tell me that distance right there. Okay? So that's going to be the height. And
what is the length? What's the length, what's the distance that it travels? Well, it's traveling in a circle, so to find the distance around the circle, we need pi times the diameter, or 2 pi times the radius. Okay, so what is the radius? This gets to Brian's question. What is the radius of that circle that is traveling around? In this case, it's x. Here's the center. X as a distance is how far from the origin I am over in that direction. So x as a radius goes, as a distance is the distance from the origin over to whatever my coordinate is. That is x as a distance. Okay.
If you were to turn around a different line, for example, x equals -1, the distance from -1 to x.
That's right. So if we were spinning it around x equals a -1, then the radius wouldn't be x. The radius would be x plus 1. We would need one more distance for any coordinate over here, any rectangle that we picked. We would take the distance of x from here over, and then we'd have to add one more to it. Okay. So it's not always x. It's not always y. Sometimes you've got to shift it. Yes. Sorry, say that again. Yeah, so, right, so if let me just grab a different color here. This is green. So if we were spinning it around this axis right there, that is the axis. Yeah. So let's look at x equals 1. If we spin it around x equals 1, then what would the distance be? Given an arbitrary rectangle or an arbitrary x, how far is it from that to the axis? How far is that? Well, I have to think about what the distance of x represents. That is from, I'm like going like this on my screen. You guys can't see. I'm like, we have to figure out this distance. So I have to figure out what the distance is. Here, x is from there to there. That's x. This distance is 1, and I really want this distance. So that's going to be x minus 1. So that would be my new radius, would be x minus 1. Okay. So we were jumping the gun a little bit, talking about how your radius changes depending on where your axes are. Is this not? My voice is hurting already. I haven't turned this thing on yet. So, all right. And I just taught a class, and that didn't help. Okay. So in the original case, what do we have where, what's going to be the length or the distance that it travels around if the y-axis is my center of rotation? What's the radius we decided? X. So it's just going to be 2 pi times x. 2 pi times whatever the radius is. Okay? And now I have enough to set up my integral, because my integral is going to be 2 pi times my radius times the height. Is height H-E-I or H-I-E? It's H-E, right? Okay. And my thickness. Okay. So all three of those things are lengths. I multiply them together. I'm going to get a volume. Okay. What are my bounds? 1 to 2. You might think it should be more than 1 to 2. It should be going to have a shape that kind of looks like that. And you might think, hey, I'm going to go all the way from a -2 to 2. Shouldn't those be my bounds? They should not be your bounds. Why not? Because I can generate the entire graph just by taking the slices over here, these x coordinates from x equals 1 to x equals 2. Right? These are the only rectangles that I need to spin around to get my entire shape. That's right. That's because I multiply by 2 pi. If I multiply by pi, then I only get halfway around. So, but I'd have another problem if I went from -2 to 2, and that problem is I would include some other volume in here. So I'm going to add way too much stuff. Okay. Okay. Any questions about shells or this problem that we just did? Yes. Oh, great question. So the function we got was x e to the x times 2 pi. You can pull out the constant, you get x times e to the x. We do not know yet how to find the antiderivative of that, but we will at 7.1. So we do what's called parts. So, okay, nice question. You might think that it's easier to do this with disks. And we could try that. You could try setting this up with disks. And if you did, then you could slice it horizontally, and you could see we've got a washer there. We would have to use 2 integrals in this case, right? Because my outer function, I've got my outer function over here. My inner function is right here. My inner function changes at this value. So I could do the bottom as 1 integral. In fact, the bottom you can do, it's not calculus. You just have to calculate the volume of the cylinder minus the volume of the inner cylinder. You don't have to do that. But you'd have to set up another integral here. And to do that, if you're doing disks, what variable are you integrating with respect to? Y? Yeah, I mean, yes, I was saying like, yes, y. You're integrating with respect to y, so you've got dy's, and this curve is y equals e to the x, so you have to solve for, solve for x, so you have a function of y. You get x equals the natural log of y, and you're going to have the natural log of y, that's going to be my radius. Oh, it's actually not going to be my radius. That's going to be my inner radius, so I need to take my outer radius, which is 2, square it, multiply by pi, minus my inner radius, which is the natural log of y, square it, dy. And you guys know how to find the antiderivative of the natural log of y squared? No, you don't. So sometimes when you're trying to do washers and disks, you just end up with something. Not only is it hard, sometimes it's just impossible. You just can't do it. So you've got to use shells. So there's 2 advantages. Sometimes you get 1 integral that's easier to do than 2, and sometimes you just can't do it with shells and washers. I know when I was in your shoes, I was much more comfortable with shells and washers. Not shells, disks and washers, and most students are. So if you've got an option, do the one you're more comfortable with. But sometimes the other one's just what you've got to do. Okay. All right. Any questions so far? All right. Okay, here's a problem I'm going to turn you guys loose on. It's the earth cap problem, except you're going to do it in shells. So that's 6.3 million squared, so that's in meters. This is the curve. This distance from there to there is 0.001 meters. We want to calculate that same volume, whatever we would get here, that region spinning around, but we want to do it in terms of shells. Okay, so we want to do it in terms of shells. Okay, does everyone understand the problem? Okay, before I turn you loose, what variable are we going to be integrating with respect to if I use this setup? We're going to be integrating with respect to x. We're going to be thinking about rectangles like this red one. Okay, so we're going to have x coordinates. There's an x distance. We're integrating with respect to x. Go ahead, you and your neighbors, see if you can figure it out. That's just the upper half. So. So. No, that'll give you this whole thing right there. So that whole thing.
So we're putting the x-axis where we're cutting. Tell us where
That's a really big 1 millimeter. Okay. So I'm picking an arbitrary x, and I'm going to try to set this up. I'm going to think about out of this arbitrary x, if I take a height and a little bit and a little thickness, delta x, and spin it around. I'm going to get something that looks like a shell. Right? So there's my shell. I need to figure out the thickness, I need to figure out the height, and I need to figure out the radius. Or figure out the radius so I can figure out the distance that it travels around. Okay? So let's start with the radius. What's the radius of the distance that it travels there? That circular path. X. So x is a distance, is right there, right there. So I'm going to have 2 pi times x like my last one. I'm spinning around the y-axis. That's really nice. X is going to be my distance. Now I have to figure out my height. That's my radius. Okay. Now I need to figure out my height. A lot of people just had this as their height. Is that my height of my rectangle? It's not. It's an important piece that I'm going to use to figure out my height, but that height, that y value, is the distance all the way down from here up to there. And I don't want all of that, okay? Unless I'm chopping off the whole Earth from the equator up. I don't know how to do that, okay? I don't have a truck big enough. So, okay. So what do I have to do to find the correct height? Subtract what? Someone raise their hand, say it really loud. Yes? Okay. So subtract the radius of the Earth, the 6.3 millimeters, minus a millimeter. Is that what you said? Okay. So I need to subtract 6.3. Oh, man. Is there a way to move this? Thing. Oh, nice. Thanks. Good job. 6.3 million minus 0.001 dx. So this right here. Okay. This is the distance up to my cut right there. So this distance right there, that's what that is. So the square root part gets me all the way up to the top. Let me put my parentheses around there. And then this other part, help make sure I keep the rest of the Earth there. Okay. And yeah, so that's the height. So this much is together, that is the height. Okay. And what are my bounds here? So I hear 0 as my lower bound, and what's the other bound? Okay, so we have to do a little math here to figure out what this point is. We need to know when does this curve drop to 1 millimeter less than 6.3 million? And so you can use the Pythagorean theorem here. 6.3 million minus 0.001 squared. I'm going to subtract that value from 6.3 million squared and take the square root. that's going to be the distance I'm going to draw in green. Okay, it's going to be this distance right there. Oh, that's not very good, huh? There. So it's going to be that distance. It ends up being about 112 meters. Okay. So is that what is that what you have calculated? So that is about 112 meters. So if you go out to the you go out to the salt flats, you go down a millimeter, slice the cap of the earth, you're going to be picking up dirt from where you're standing to 112 meters away. So more than a football field in each direction. That's how big the circle is you're going to be leaving. So our upper bound, our upper bound is going to be x equals 112, x equals 0. Okay? Now, why not x equals a negative 112 to x equals 112? I have volume for all of that, right? Why don't I go from x equals negative 112 to x equals 112? Right there. Nice. Yeah, so we think about where are the x coordinates? What are all the x coordinates where I'm going to be spinning those rectangles around? And those x coordinates, it's the x coordinates of this region right here. I just have to spin that region around, and the x coordinates are just going to be from 0 to 112. So that's enough. That's if I go from minus 112 to 112, then I'm spinning the left-hand side around too. I'm going to end up with twice as much volume as I really have. Okay. Good. Questions about this problem? Yes. How did I get the bounds? Okay. So this is the radius. This distance from there to there is 6.3 million meters minus 0.001. And then I just used the Pythagorean theorem. So to figure out what this distance is. So that's r squared minus 6.3 million minus 0.001 squared, and take the square root. And that's what that distance will be. So, and that's the one thing that ends up being about 112. Yes? Yes, that's exactly right. That's another way to think about it, is you can set your curve back here. You can set, you want to know, when does this thing here, when does that equal 6.3 million minus 0.001? So, and then you can solve for x. Yes? Yeah, yeah. So you were using it over here? Yep. So if you set it up over here and you're going to do shells, what variable are you going to be integrating with respect to? That's right. So you're going to be integrating with respect to y, because your slices are going to look like that, and you're going to spin those around like that. So good. Yep. Okay, other questions? All right, let's do another fun problem. I know you're thinking every time a professor says fun, you're thinking hard. So Okay, so here's a function in terms of y. X is a function of y. We're going to spin that around the x-axis. Okay, so you've got a region. You can spin it around that. So go ahead and work on that. You can work on it with your neighbor. Yep, the upper limit is the square root of pi. Lower limit is, would be 0. This was X. If you're able to set this up, you should actually try to calculate it. Try finding the antiderivative. Okay, I'm going to start walking through this. We've only got about 5 minutes left. So I'm thinking first, I want to figure out what my radius is. So my axis is my axis of revolution is the x-axis. I'm integrating with respect to y. I'm integrating with respect to something that's parallel to my axis. So I'm going to be using shells. I'm integrating with respect to y. Oh, by the way, this is an impossible problem to do with disks. You can try chopping it up in terms of x, but then you've got to solve for, you've got to do some crazy trying to solve stuff. Well, when you can solve for it, you just can't integrate what you get. So you can't find an antiderivative. All right, so what's my radius? My radius is going to be the distance from my axis up to my arbitrary y, which is just y. So my radius is going to be y, so 2 pi y will be my distance around. And then what's my height going to be? What's the height, or in this case it looks more like a length, of my shell? What's that going to be? What's this distance going to be? sine of y squared. It's an x distance. Right? This is an x distance. How do I find that x? I take whatever y coordinate I'm at, I plug it in, I square it, and then evaluate it with the sine, and it'll tell me that distance. Okay? So, so my height will be sine of y squared. That's the height. That's the radius. And what's my thickness? dy. Now, y equals, what are my bounds going to be? 0 to the square root of pi. Why? I'm not going to go from a negative pi to the negative square root of pi all the way up to the square root of pi. I'm not going to do that because I just need to take the slices right here of this region and spin all those around to generate my entire solid. Okay, so I just have to spin the slices from x equals 0. I'm sorry, from y equals 0 to y equals the square root of pi, and that will give me my bounds. Okay, questions? Yes. Oh, so actually do the antiderivative? Yeah, so how are we going to actually calculate this? U sub. So 0 to the square root of pi. I'm going to pull out my 2 pi. I have y sine of y squared dy. U equals y squared. Du is 2y dy. I have a y dy. Oh yeah, and I have it too, so I could do that. I'm not going to be as tricky. So I've got a y dy. I'm going to solve for y dy and get du over 2. So then my y dy just becomes du over 2. My y squared becomes u. And I have 2 pi, 0 to the, oh, whoa, just I made a mistake, right? Let's change this in back terms of u. So u equals, when y is 0, u is 0. When y is the square root of pi, I get u equals pi. So u equals pi. I can divide out my 2's. So I need to find out what the antiderivative of sine of u is. What's the antiderivative of sine of u? Negative cosine of u multiplied by pi, evaluated from 0 to pi. Have I missed anything yet? So minus cosine of pi minus a negative cosine of 0. Cosine of 0 is 1, so this whole thing is 1. So I end up with plus 1. And cosine of pi, negative 1, so it's minus a negative 1, so that becomes positive. And I end up with 1 plus 1, which is 2. Just feels funny saying that in a calculus class. 1 plus 1 is 2. So I end up with 2 pi. All right, have a great day. Have a great weekend. Life is good.